Morning, very good morning to all. The discussion of charged particle in an electric field. Hope you enjoyed the topic. The concept is very important. Let me tell you, it is very important for all the types of our examinations. Key concepts. In that we have began with the simplest case, charged particle placed in an electric field. We have taken U to be 0. Now we follow the other cases now, but even when we are following the other cases, I'd like to remind you two important things. The first one is, see, it is writing F is equal to EQ and then A is equal to EQ by M, the acceleration term. And what is the direction of force and acceleration. Afterwards, what we have followed is our understanding of the kinematics equations, motion with the constant acceleration, because when we are writing this F is equal to EQ, remember we have taken the case of uniform electric field and hence the force is a constant force and acceleration is also a uniform acceleration. So for which we have made use of our first year knowledge of writing velocities, writing energies. Now today's session you will have more fun and more interesting things regarding the same charged particle in an electric field. What is that? Let us see. Be ready with your pens and books. Now we consider the case of charged particle projected, thrown in a uniform magnetic field. Same terminology, remember? Particle mass M, yes, charge small q I am using, and electric field strength capital E, the electric field. Now, this is the case of particle projected in the electric field such that I have taken, it is projected with a velocity U. U bar is its initial velocity. Now, different cases that arise in that, the first case is U bar parallel to E bar. The charged particle projected parallel to electric field. Parallel to electric field. Now, first, as I have told you, to write the force and acceleration, the same steps we follow. F is EQ, independent of mass, depending on the charge and field, and hence A is same, EQ by M. In fact, I would like to do it in complete vector notation so that it will be too good. But I then thought the student may feel difficulty if I start using the vectors. And that is why I will do all in this, I will show all of them in the scalar form. But the best thing is to do it in the vector form, right? Now, force and acceleration, we know the direction. For a positive charge, it is along the field, and negative charge opposite to the field. Therefore, now comes the question, when a charged particle is projected in an electric field, whether it is positive charge or negative charge is the question. Therefore, now I am writing in this, the first case is for plus Q. Now you tell me what happens, positive charge, see, charge already projected in the direction of field. Now positive charge accelerates in the direction of field. What does it mean? Yes, the velocity of the particle increases. The particle keeps moving in straight line. Remember, the particle keeps moving in straight line. Now I am writing for plus Q, it is uniform acceleration. Uniform acceleration, yes, along field, along E bar, such that, what is the case we are taking? Velocity increases. Why velocity increases? Yes, it is acceleration along the field for the positive charge. Therefore, if I am writing a velocity after t seconds, then it will be in this form, V is equal to U plus AT. A means EQ by M times T. Now this is I have given for positive charge. Now what about negative charge? Right? So if I am writing the case for negative charge, it is now your turn to use all your simple common sense. So now I am writing this for negative charge. For negative charge, what happens? Negative charge always experiences force and accelerates opposite to the electric field. Therefore, now in this case, for minus q, yes, it is uniform acceleration. In fact, if I write it in a very loose word, I will call it as retardation. Why? Why retardation? Why retardation? Because force is opposite to the direction of motion. See, there I have shown this u bar vector towards your right hand side, and now the force or acceleration is towards your left hand side. That force is opposing the motion of the charged particle. Here what do you understand? The force is supporting the motion and hence velocity gradually increases. Whereas here the uniform acceleration is retardation and therefore the velocity gradually decreases. Velocity, yes, gradually decreases. Remember, one thing is that here we have taken a field over a very large region, right? As long as the charged particle is in the space of the electric field, so long there will be acceleration, right? Once it comes out of the electric field, what happens? No question of force and hence no acceleration. That is, afterwards velocity remains constant, maybe no, in both magnitude and direction. In all such cases we are discussing, yes, this electric field is up, in a very large space, and we always consider the charged particle moving in that space. Now here the velocity gradually decreases, therefore for such case, yes, V is equal to, it becomes U minus AT avenues. V equal to U minus AT avenues, therefore this becomes U minus A means, yes, EQ upon N times T. Now here what is the possibility that you can tell me? Just imagine yourself. Now supposing it is a negative charge like electron projected along the field, what happens? Velocity gradually decreases. So when it is the case of velocity gradually decreasing, at some instant after some displacement, its velocity should become zero. Instantaneously. Instantaneously it becomes zero. Once it becomes zero, what happens? Because of the force opposite to the direction of the field, now the particle starts retracing its path. I said it retraces its path. There is a possibility, as I have told you earlier, when I consider the field over a large space. Now here you see what happens. If this is what is a negative charge, suppose this is some negative charge projected, velocity gradually decreases. Supposing velocity becomes zero at this point. Even this point is, yes, well inside this uniform electric field. Now at this point velocity is zero. Now what happens, you tell me? Since velocity has become zero, now it earlier moving from A to B with retardation. A to B with retardation. Now retraces the path I have told you. Therefore now it starts moving from B to A, and that will be with the uniform acceleration. Is it not? Positive charge, yes, keep on accelerating in the direction of the field. Gradually velocity goes on increases. Velocity goes on increases means it gradually gains kinetic energy. It keeps on gaining the kinetic energy. That will be the case with positive charge, whereas with the negative charge we have another possibility also, as we have explained, A to B retardation and then retracing the path from B to A with uniform acceleration. Now this is the discussion I have made for U parallel to E bar, in which again we have the cases of positive charge and negative charge. Now the second case you will discuss on your own, is it not? What is that case? This U bar opposite to E bar. Supposing the charged particle is projected opposite to electric field. Opposite to electric field. Now you tell me what happens? U bar, yes, opposite to E bar. Opposite to E bar. Right. Now it will be a very common sense thing for you. Whatever we have told for U bar parallel to E bar for both positive and negative charges, now exactly a kind of reversal that we find in the complete phenomena. Now here I have shown this is the electric field and charged particle is projected like this with velocity u bar I mean to tell. So this is the charged particle. Now what happens? Now here the case for positive charge. Earlier whatever happened with the negative charge, now the same is case with the positive charge. Therefore now I simply say this is for plus q and this is for minus q. A simply reversal of the cases. Whatever earlier happened with positive now happens for negative charge and vice versa. So when it is the case of looking to the charged particle projected, first point you should be looking at is the direction in which it is projected. We are now taking the case of, say this is u bar opposite to e bar means the angle between the vectors is 180 degrees. Earlier we said u bar parallel to e bar means angle between the vectors is 0 degrees. So we have discussed the cases of 0 degrees and 180 degrees. And remember, this is important with respect to the nature of the charge. You have to look at those, look at that particular specific charge, whether it is positive charge or negative charge. Now, using this concept of charged particle, either placed or projected parallel or anti-parallel to the field. Now we define one important parameter, one important unit I can say. What is that unit and why we need it? Let us see. Same discussion, same understanding with a simple vector notation. Because this makes afterwards the so-called the complex things easier because of this concept of vectors. What is that? Earlier we have told electric field, E bar vector, and then a vector U bar vector, the initial velocity vector we have taken, such that there are two cases that are possible, like E bar parallel to U bar, or U bar parallel to E bar, or U bar opposite to E bar. In all such cases, now you see how I am making the things as a simple vectors. Now, if I take the field vector I am writing, right? The field vector is E I cap. I take E I cap. That I have taken the field along the positive or x-axis. Positive x-axis. Then let me also take U bar or velocity taken as U I cap. So this is E I cap, U I cap, that is what is I mean by parallel, it is equal to 0 case. Now here comes for positive charge and for negative charge. Now here for this positive charge, F is equal to, or I will write F bar is equal to E Q times I cap, because for positive charge along the field, and now here we write it F bar is equal to, yes, the magnitude is of course EQ, but it is anti-parallel to the field. So that is how I write it, the force. And similarly here the acceleration term also the same, EQ by M times I cap. This is where force and acceleration for positive charge along the field, and this is what is force and acceleration for negative charge which is anti-parallel to the field. Because if this is simple understanding of this, afterwards whenever we take up other cases like motion in plane other than angles like 0 or 180, those cases we can do without any confusion, right? So now let us see how this vector notation we will implement for the other case. Now I take the case like theta is equal to 90 degrees. Earlier we did with 0 degrees and 180 degrees. Now let us take the case of 90 degrees. So the same understanding of kinematics, is it not earlier all our discussion? And I have told you, no new physics in second PU. And I want to prove it every day, every session till the end of our syllabus. Day 1 to day last, It will be almost like no new physics except one or two topics somewhere, very rare cases. Now, you remember what we did in first PU? We have a very popular and interesting case of what is called as the projectile motion. You remember? We have told about these cases, right? An object, a ball, thrown from the top of a tower. Suppose a body is projected horizontally from the top of at a height above the ground. What was the result? You remember? Now here when we have discussed this case, we have considered one force. What is that force? And acceleration. That is what is acceleration due to gravity, which always acts vertically down. So this is what is the acceleration, and that is why we said, now this is what is u. Now remember, suppose I take this as x direction and I take this as y direction. Now what was our discussion? I just remind you one time, because now we have to duplicate the same things. All the first year concepts will have a duplication in second PU with a simple change in terminology and the symbols. Nothing new you will find actually. Now here in this case, ux is given to be u because all the velocity is horizontally, and therefore uy is 0, no question of any acceleration initially in the vertical direction. And now here, we know that the force is acting downwards. Horizontal motion is not affected by vertical force was the principle, at least by work energy theorem also, because definition of work says W is equal to F S cos theta. But theta is equal to 90 degrees, W is equal to 0, no change in kinetic energy. It means that whenever motion and force come across, we come across, if the motion and force are perpendicular, then the motion is not affected, the speed is not affected, we say. Now here, the same is the case, uy is equal to 0, but ax is equal to 0. No acceleration in the horizontal direction because gravity acts vertically downward direction. Even if you take the component, you know what is that? If a is a magnitude, a cos theta becomes the component, for theta is equal to 90, even that component becomes 0. Therefore, horizontal velocity is not affected by gravity. Remember, ax equal to 0, and now ay, this is what is g, which is acting vertically down. And that is where what happens, it has two-dimensional velocity, one-dimensional acceleration. That is the case here we got, right? Two-dimensional velocity, one-dimension acceleration. The path is not a straight line. The path is a very popular parabola. Because you know, at any point now, at any point in the trajectory, you will find that velocity is always tangential. Suppose at this point, if v is the instantaneous velocity, then we have two components that is resolved. This component is Vx and this component is Vy. This horizontal component not affected because Ax is equal to 0. So horizontal velocity remains the same throughout. Therefore this Vx is equal to u. Again write it as u only. Vx, yes, that is Vx is equal to ux, that is always equal to u. Whereas V, initially it is 0, but afterwards later because of the gravity, velocity gradually increase in the vertical direction. And therefore V also we get velocity time. If you take V is equal to u plus at, u is equal to 0. Therefore now you get Vy is equal to gt. So it has two-dimensional velocity, one-dimensional acceleration. Therefore, when it is ux and vx and vy, two velocity component, what is the velocity of the particle? Yes, velocity of the particle is now given by v is equal to root of vx square plus vy square. This is what was our discussion. We made all these things in our first page, remember? Right? This is what is the instantaneous velocity at any point in the trajectory. Likewise. Not only this one, you remember? This we call it as a horizontal projectile case. Even we have discussed earlier the case of oblique projectile. There also two-dimensional velocity, one-dimensional acceleration, a very beautiful discussion is done in our classroom for all those time periods or time of ascents, time of descents, time of flights, ranges and relations between them. We all did. In that discussion, their acceleration A was G. Is it not? The discussion happened like this. Now the same discussion I would like to do with the electric field as well. How? See, now I am taking the case of theta is equal to 0 degrees I am discussing. Projected such that theta is 90 degrees. Again, we will discuss the positive charges, negative charges, and all this discussion will go on. Now, come to this discussion. Now, here you will find electric field. I have shown vertically upwards. Supposing if you want to write a vector, I will take that vector as j cap, because y direction I take, horizontal direction I will take it as I cap. Okay, like that. Now you see, this is what is an electric field, and the particle thrown or projected into the field. Now the field begins at this point. Field begins at this point. Now, this is a positive charge projected. So what happens? As soon as this enters the field, as soon as the particle enters the field, it experiences force such that positive charge along the field. Now initially it has velocity in the horizontal direction, and the force or acceleration is in the vertical direction. Therefore, horizontal velocity, you just duplicate that principle here. Horizontal velocity, suppose here I say u, it continues the same everywhere. Whereas vertical velocity initially 0, it starts increasing. For positive charge, it is along. Therefore, now the same case, the path will be a parabola. Parabola like this I am showing. This is what is the parabola that we get. Now you see the trajectory is along the field we are getting. Along the field we are getting. Now here, if it is P is an instantaneous point, if P is instantaneous point, now what is the same discussion that carries? Here we have taken Ux is equal to U. Again, Ax is equal to 0. No acceleration in the horizontal direction. Whereas in the vertical direction, no velocity. Uy is equal to 0. And Ay, what is that Ay? Eq by m. In all such cases, of course, we are using that common. What is that acceleration? A is equal to Eq by m. The force which is Eq, and the direction, of course, we have been using now for so many times. Now at this point B, there are two velocities again. So this is what is the Vx component, and this is what is Vy component at this point P. Now what do you write again? So again, our discussion, duplication, I said Vx is equal to simply U. And what is Ax? Ax is 0. Upwards, what is Vy? Vy is equal to V is equal to U plus AT if time relation is given. V is equal to AT. In the place of A, I will use, yes, this is what is Eq by m times T. Eq by m times T. So this is what is Vx and Vy. Now what is the total velocity of, the instantaneous velocity of the charged particle, right? So this is how we have calculated. Now you see what is the path that we have got. We have got a parabola. A parabola, most important thing is that the trajectory is along the field for positive charge. Now, yes, your common sense says, supposing if it is a negative charge, I am writing it for negative charge. Negative charge experiences force and accelerates opposite to the field. So one more time, the same case of two-dimensional velocity, one-dimensional acceleration. Again, the path is parabola such that you will see the trajectory is opposite to the electric field. Now we can actually continue our discussion and write many other things also as well. But I stop at this stage because once we come back in our direct interaction, the learning will be two. At least till that time, your understanding about the projection of charged particle with different cases, with those two to three fundamental ideas, you be ready. Now I hope it is clear. Particle projected if theta is equal to 90 degrees, the path is parabola. The path is parabola. Now here you remember, whenever we have taken the case of charged particle in a uniform electric field, there are only two possibilities with respect to the path followed by the particle, right? So for a charged particle in a uniform electric field, I underline this point, uniform electric field, because afterwards sometime later we may discuss for our other examinations the case of non-uniform electric field. But here you can see it is only the case of uniform electric field, right? Charged particle, uniform electric field. Trajectory, only two possibilities. What are that? It is either straight line or parabola. Only two possibilities are there. Second point. Remember, whenever it is straight line, it is not with uniform velocity. So, a charged particle, electric field, no question of uniform velocity. It is always uniform acceleration. And when we say the uniform acceleration, again it can be velocity increasing case or velocity decreasing case, which we in loose terms called as retardation. So it is either velocity increasing along the field or velocity increasing opposite to the field or decreasing opposite to the field, increasing opposite to the field, all such possibilities. That is what is the case. Only two possibilities and no question of uniform velocity. In the trajectory also, straight line or parabolic trajectories, the kinetic energy always changes. Kinetic energy either increases or kinetic energy either decreases. We can formulate good number of 1 mark, 2 mark, CT, NEET conceptual questions. When is the case of gain of kinetic energy? Now supposing if I put you a question, a very generalized question. When does a charge gains kinetic energy in an electric field is the question. So what will be your answer? What will be your answer? Different possibilities. If a positive charge is projected along the electric field, then it gains kinetic energy. If a negatively charged particle is projected anti-parallel field, it gains kinetic energy. And also remember, if a charged particle is projected into an electric field at right angles, then also both positive and negative charges, they gain kinetic energies. And when will be the case of loss of kinetic energy? So like this, good number of questions conceptual. If numbers are given, they become very, very, very complex examples as well, right? So that is why after you come back, we'll do all such different cases. But before that, make sure you are very good at your concept, right? Now let us take up one more topic. This was our discussion for the case of charged particle placed or projected in an electric field. Now comes the question. Let us take a dipole, and dipole placed in an external uniform electric field. Very beautiful study that we come across. Remember, the study is new, but many duplications of our first year concepts. Let us see that. From a single charge to the case of an electric dipole placed in an external uniform electric field. A very popular case for all your board examinations. Follow this physics part. I tell you, every time we draw a good, beautiful, you may call it figure, but I keep calling, that is, I keep telling you, that is what is the entire physics. We need to practice and we need to understand that part afterwards. Your English and your common sense. Writing answers for board examinations becomes so easy. Remember, you're all 17 years, 18 years boys and girls, and please try to avoid this habit of following Xerox copies or the notes of somebody or some, you call whatever material. They never help you. They never help you in your future academics, or even they never help you for any of your happiness even in the examination. Because writing notes or doing derivation or definitions, everything will be there in our physics. Now look at this. A dipole placed in an electric field. I have shown a situation. This is a uniform electric field. I have shown AB, a dipole, placed in the electric field at an angle I am showing. This is what is theta. Now when I said theta, what is that angle theta? It is angle between P bar, the dipole moment of the dipole, and E bar. The angle between P bar and E bar. Because we always know that P bar is along the axial line, right? Minus Q to plus Q, what you write. Therefore, this is minus Q plus Q. P bar and E bar angle is theta. Now, this is what is your simple notes as well. Consider a dipole. Consider a dipole of length 2a, and a dipole moment small p, placed in a uniform electric field at an angle theta. Maybe in the bracket you can write angle between P bar and E bar is theta. Now by principle, every charge will experience force in the electric field. Therefore, this positive charge at the site of B and negative charge at the site of A, they will experience force. So let us write force and see what will be the consequence of that force. First, let us show these forces as vectors. Now this is a positive charge experiencing the force F equal to EQ, and as usual always parallel to E bar because of the positive nature. Therefore, this is what is the vector I have written. This is force due to force on the positive charge, and therefore this will be the force on the negative charge. Remember, whenever we are taking the case of electric field, we consider it as a large space. Now these are the two forces that are experienced. Let us now write the individual forces and hence the net force. Therefore, now I am writing by principle, each of the charge, okay, now there are two charges, positive and negative, each of the charge experience a force. Now let us write force on positive charge is F plus Q. The symbol I have used is nothing but simply the definition. E times Q, the intensity times the charge, and what I have told you, yes, that is important. This is along E bar. This is along E bar. Now you will see this will be a very famous, popular 3 marks, 5 marks question. We call it derivation. All the derivation notes is there in that beautiful representation. Please, you follow that. Give a pause to your video. Watch that figure one more time for few more seconds, you observe that. What is the field? How the dipole is placed? What are the different symbols that we are using, right? Force on positive charge, and now comes the force on minus Q. F due to F on minus Q is again, I am writing it as EQ, but this time I say opposite to E bar. So now we see that these are the two forces acting along different lines of action. Come to our figure one more time. What is meant by line of action? Yes, the direction in which force exerts, that what is called a line of action. In this figure, what you observe, this is the line of action, and this is the line of action for the two, right? They are equal, opposite, along with different lines of action, right? Therefore, what will be the net force? Net force, yes, because of this equal and opposite nature, the net force is yes, it will be the vector addition, anti-parallel nature. Therefore, EQ minus EQ minus EQ, that is what is 0. No net force. No net force means no way it is affected in the translatory sense. No force, hence no translatory motion, no linear motion, no translatory motion. Earlier we have seen when it was a case of a charged particle, yes, due to force and acceleration, there was acceleration, right? It was a straight line or a parabola. Motion was affected. But here what happened? There is no translatory motion. Please underline this point. For the dipole in uniform electric field, no translatory motion. Now, one more time. In the very beginning, I have told you it is simply duplication of all our first year understanding, right? Now, here what you find is that these are the two forces acting. Forces equal, opposite and acting along two different lines of action. Such pair of forces is what is called as couple. Is it not? Now, F due to F on plus Q and F on minus Q, they form a couple. So that's what I am writing now. Now, since F on plus Q and F on minus Q are equal, opposite, and what is the third character? Along different lines of action. Different lines of action. Almost I am writing complete notes for you on the board. Right? Different lines of action, hence form a couple. Hence form couple. Different lines of action, they form a couple. Now, what is your understanding in first PU? Whenever we come across a couple always produces torque. What do we mean by torque? The rotational effect caused by a force is what is called as torque. And couple always causes torque. And torque always gives rise to rotatory motion. Therefore, earlier we said no question of translatory motion, linear motion for the dipole. Whereas now dipole in uniform electric field experiences rotatory motion. And hence dipole rotates. Hence dipole rotates. Now two things will add to this. How much is the torque? Now we will calculate again using the same geometry which is there in our complete physics representation. And what will be the purpose of the torque? Two things we will discuss. Remember, what is, how much torque it experiences now and what will be the purpose. Let us see that. Let us see that small mathematical discussion. Now these are the two lines of action. Now I draw this perpendicular line between the lines of action. This is a perpendicular that is drawn. I call this point say C. I call this point C. Then this BC is what is the perpendicular distance between the forces. So BC is, yes, the perpendicular distance between the forces F on plus Q and F on minus Q. And one more important, so let us show this geometry here. Notice that AB nothing but length of the dipole 2A. And now this is what is the angle that is theta here, right? So for this theta, how to write BC? You will see. If this is what is theta, yes, this is also happens to be theta. Therefore, here sin theta if you take, because for this theta this happens to be the opposite side, right? So sin theta is BC by AB implies BC, the perpendicular distance is AB times sin theta. What is that AB? 2A. Therefore, this is BC is equal to 2A sin theta is one important thing. So when you have given this representation, along with the representation, please always remember. Earlier maybe I might have forgotten, but during your notes, during your examination, you never forget to mention all the geometry in our representation. So this is geometry, right? Use the definition of torque. Now, by principle, by our definition of rotatory motions, by principle, torque on dipole is, right? First let me show it as a simple scalar form only. Now this is what is tau scalar only. Tau is equal to force times the perpendicular distance. This is how we have defined. I told you the same duplication. Now change of terminology I said. Now here that force is of course EQ, each of the force, and the perpendicular distance is 2a sine theta. 2a sine theta. Small rearrangement of terms I will do. So this is rearrangement. Tau is 2a cube. Then this is E. Then this is sine theta. Is that okay? Simple rearrangement of them. 2a cube. This E term and sine theta. Now comes, what is this 2a cube? Length of the dipole multiplied with one of the charges. Not charge of the dipole, because charge of the dipole is always 0. Length of the dipole times one of the charges is the dipole moment. Therefore, the final result is tau is equal to dipole moment P times electric field capital E times sine theta. This is how we write. Now we know that this torque is a pseudo vector. Is it in rotatory motion? Whatever vectors that we got from angular velocity, angular acceleration, angular momentum, torque, all these are pseudo vectors. Therefore, if I am writing this as a pseudo vector, so this is what is tau bar is equal to, see here, a d sine theta form you have, etc. Therefore, I will write it as p bar cross e bar is the vector form. Remember, this order is important in all the cases of cross product. The rule, the order that you got this time is P bar dipole moment vector first, and then the field vector, So this is what is the expression for torque experience. And this torque, of course, as usual, it can be either clockwise torque or anti-clockwise torque. Remember, these are all the things that we have discussed with good details in first PU. Torque can be either clockwise torque or anti-clockwise torque. Now look at this, our present representation. What type of torque do you expect here? Now these are the two forces that are acting, and the torque will be in the clockwise sense you will get here in our discussion. This is what is clockwise. When do we get anti-clockwise? Supposing, you see, one more time I show you here. Supposing if, don't always think that the field should be like, horizontal lines. I will show, supposing this is what is the field, this is the electric field, and I have placed a dipole like this, and this is what is minus q, and this is what is plus q, this time. Now one more time, draw the force vectors. Now this is what is force on positive charge, and this is what is force on minus q, right? And therefore this again will give rise to a clockwise. When it will be the anti-clockwise, right? Supposing I change the direction of the field. I change the direction of the field and place like this, plus q and minus q. Now here what happens? Let me take this as plus q and this as minus q. Again, these are the forces that you got. And this time, this is what is the anti-clockwise torque that you are getting. So when you are writing this, tau is equal to P sine theta. Other than board examination, supposing if it is NEET examination or JEE examination, it is most important point to look for the order of the torque, whether it is clockwise torque or anti-clockwise torque. Why? You will come across when we do some beautiful example. Right? Tau is equal to P sine theta. Now shows that the torque depends upon the angle. Again, come back to this point. What is theta? Theta is the angle between P bar and E bar. P bar dipole moment vector and field vector. That is what is the angle. Now we will discuss those some interesting cases. What is that interesting case? Tau is P sine theta in the scalar form I have taken. For few special angles, I will discuss about the torque. Of course, you will do it now. Simple mathematics. Tau is equal to P sin theta. Even before that, first let's come back. Y torque on a dipole. Y torque on a dipole. You see here, because of this clockwise torque, what happens? Finally, rotation comes and the dipole will come in the direction. That is, P bar becomes parallel to E bar. So what is the purpose of the torque? Why the field exerts torque on the dipole? Means to align the dipole in the direction of field. In the direction of field, adu bandidbeku. Is it at any other angle it has, the field does not allow. It always asks the dipole or tends the dipole to align in the direction of the field. The same happens in our classroom also. In the classroom, many times I have told you a Vidyarthi should come, or Vidyarthi should be, or Vidyarthi will always be in a mood of learning. In the mood of learning. But we know that if it is not the case of mood of learning, your teacher always compels you to come into the direction or come into the mood of learning. Is it not? The same here also happens. Torque always, right, tends to orient the dipole, aligns the dipole in the direction of field. That is the purpose. Now tau is equal to P sin theta. I am discussing this case of theta is 0 degrees. Theta is 0 degrees. Of course, mathematically we will say sin theta 0, torque is 0, tau is 0, torque is 0. Torque 0 always says rotational equilibrium. Remember, earlier also we have discussed some equilibrium cases. Now here, what type of equilibrium? In the case of translatory motion, we said net force is equal to 0. Then it is what is the dynamical equilibrium or static equilibrium. But here now we find that torque is equal to 0 always refers to rotational equilibrium. Friends, I repeat, equilibrium, different types of equilibrium that we come across in physics, right? Rotational equilibrium, torque 0. Now see, the point is, tau is equal to theta equal to 0 degrees. What will be the orientation? How the dipole is placed now? That picture is important. You know that you should write on your own, because already I have told you what is the meaning of that theta, angle between P bar and E bar. Therefore now this time, supposing if I tell you this is the dipole, minus Q and plus Q, and this is what is the field E bar. Now tell me whether theta is 0. Theta is 0. First write the vector. Moment vector is always from minus Q to plus Q, right, along the axial line. Therefore, this is what is the moment vector that you get P bar. Now you see these two P bar and E bar, they are anti-parallel. Theta is not 0 here. So for theta to be 0, what is the orientation or what is the alignment, right? So your understanding from such very, maybe it may look trivial, but they are very important, which speaks about the strength of our concept. Therefore, this is what is minus Q and this is what is plus Q placed like this. Now theta equal to 0, tau equal to 0, and it is a rotational equilibrium. Now let me take the other case of theta is 180 case. Theta is equal to 180 degrees. Theta is 180 degrees. What happens? Again sin theta 0. Again sin theta 0. Therefore again tau is equal to 0. Again the case of rotational equilibrium. But again the orientation, yes, now this time I can see you have your picture. How this is the field E bar vector, and alignment or the placement of the dipole is like this. This is minus Q and this is plus Q. This is the representation of theta is equal to 180 degrees. So both 0 degrees and 180 degrees are equilibrium conditions. Remember, Couple of days back in our sessions we have discussed the case of whenever it is equilibrium, we are talking about the static or rotational equilibrium, there comes the question of stable equilibrium or unstable equilibrium. And I have told you already the definitions or the understanding of that stable and unstable equilibrium. Now here, theta is equal to 0 degrees. Once it is in equilibrium, now I just slightly have a small disturbance. I change the alignment. Supposing if I change the alignment to this position, what I have told you that whenever there is angle other than 0 or 180, what happens? Torque will act such that, what is the purpose of the torque? Torque always tends to align the dipole in the direction of the field. In its own direction it aligns. Therefore, even if we are slightly disturbing the position, again it will come back to same equilibrium. Again it will come back to same equilibrium. Therefore, theta is equal to 0, rotational equilibrium. This time it is a stable equilibrium. I underline this point. Theta equal to 0 degrees. Now comes this question. Minus q plus q. It is in equilibrium. Yes. Supposing you have a small slight disturbance such that this is minus q and this is plus q. Now what happens? Tries to, yes, bring the dipole in its own direction, the field tendency. Is it not? Therefore, after this, the new position that it looks like is after slight disturbance of the equilibrium position. Yes, this is what you find. Minus q and plus q alignment will come like this. What does it mean? A disturbance of the equilibrium, it is not regained. There the equilibrium is regained. No question of regaining. Therefore, it is the case of unstable equilibrium. Therefore, for theta is equal to 180 degrees, the equilibrium is, yes, I do mention here, unstable equilibrium. Because this is what is your examples for board or CT or NEET examinations. He says the position, he says stable equilibrium position, unstable equilibrium position. There you need to substitute the theta values as 0 degrees and 180 degrees. Unstable 180 degrees, stable theta equal to 0 degrees. Now you see what is that case 3 that you can talk. The case 3 is theta is equal to 90 degrees. Theta is equal to 90 degrees. Then torque becomes maximum, tau becomes maximum. Why? Because sin theta happens to be 1. Now don't argue with me what about 270, it is the same case, right? Odd multiples of 190. Tau maximum is equal to, you will get it as P times E. P for dipole moment. So tau maximum is equal to PE for theta is equal to 90 degree position. Now, this third case I will use it for one definition. Earlier when we have introduced this concept of dipole, we have said dipole moment as the product of dipole length and one of the charges. But that it is not a true definition of dipole moment. Now, this is the time I define dipole moment. So whenever if a question is there, what is dipole moment? Please, for God's sake, at least as a Vidyarthi of Paniras, don't write it as the product of dipole length. Now you see what is the definition of this dipole moment. In fact, if you remember, I have given you a small technique I can call to define a parameter in physics or a unit in physics. A small technique that I have given using the mathematical expressions which we call equations or formulae. Right? What is that? You see here, tau is equal to PE sin theta. Now, I am writing a condition, a special condition such as for E is equal to 1 unit. E is equal to 1 unit. Theta is equal to 90 degrees. Of course, as earlier said, tau maximum for theta is equal to 90. Theta is equal to 90. Then this tau maximum is equal to P. Now this is our definition of dipole moment. Now going in reverse order. Dipole moment is maximum torque experienced by the dipole when placed in a uniform electric field of unit strength at right angles. 90 degrees is there, therefore I call it as at right angles. Now English part, I don't write. Please listen to my statement and make it into your notebook. What is the definition of dipole moment? The maximum torque experienced by dipole when placed in a uniform electric field of unit strength at right angles is dipole moment. Is it done? So this finishes the beginning topic of a dipole placed in an electric field. We discuss about the rotational effect in the form of torque. Now, the same topic with a small improvisation, with small additions, will continue in our next class. Today's session, one more time, you remember, we have discussed a very popular case for our competitive examination, like charged particle projected in electric field. What are the different possibilities? What are the different consequences? Right? And one more important thing is a regular case of dipole placed in electric field. Let us continue with some added things in our next session. Till then, enjoy your rainy days with good food and good preparation. Good day all of you.